Question 6. You throw a ball vertically on Earth and it reaches a height of 20 meters. What would be the height it reaches if thrown vertically on the moon, where gravity is 1/6 that of Earth? Okay, so let's see. What can we know? Well, the one that's on Earth. Okay, we have initial velocity, a final velocity, an acceleration, and a time. I know that the change in y, it says that it reaches a height of 20 meters. That's its maximum height. So the initial velocity given to the ball, I don't know. But I know the final velocity. If that's the maximum height, then the final velocity must be 0. I do know the acceleration of the ball on Earth. That's 9.8. And time I don't really care too much about. I want to have this exact same ball being thrown the exact same way on the moon. So what I want to know is how much initial velocity did we give the ball, and then I can do the same thing with the moon. Okay, so let's solve for initial velocity, which means the one thing I don't care about is time, which is our fourth equation. Vf squared is equal to Vi squared plus 2a change in y. Well, Vf is 0, so I'm going to end up with a Vi squared plus 2 times this negative 9.8, and that will give me my change in y. Change in y, sorry, is 20. Okay, it's 20. So we will have 2 times the negative 9.8 times 20 gives us a negative 392. Okay, so I'll have Vi squared minus 392. Add that 392 to the other side and then take a square root. Okay, and if we do that, we end up that Vi had to be 19.8 meters per second. Okay, so you had to throw the ball with an initial velocity of 19.8 meters per second in order for it to reach that height of 20 meters on Earth. Now let's jump over to the moon. How high does it go on the moon? We don't know. That's what the question is asking, right? What's the height on the moon? But if we do the exact same throw, I'm going to throw it at 19.8 meters per second. Final velocity, I want the maximum height, so I want that to be 0. And the acceleration on the moon, it says gravity is 1/6 that of Earth. So I'm going to have negative 9.8 divided by 6. And again, time is the thing I don't care about in these ones. Okay, so I need to plug in now, and I need to find out what this change in y is. Again, we don't care about t, so let's use that same equation. Vf squared is equal to Vi squared plus 2a change in y. Vf again is 0. Vi, we now know, 19.8 squared. Plus 2 times acceleration in this one, negative 9.8 divided by 6. And the change in y is what we're looking for. Okay. So now we got a little calculations to do. This is going to be a very large number, and then this one over here we're going to have as well. So let's figure out what these are. Let's start off with the 19.8 squared. This will be 392.04. And then, of course, this one here, the 9.8 times 2 divided by 6 is the same as dividing by 3. So we're going to get a negative 3.26 change in y. Okay, so now I'm going to minus the 392 to the other side and get negative 392.04. And then I'll be left with a negative 3.16 delta y. I'm going to divide both sides by negative 3.26, and that will just leave delta y. Okay, so the negatives on that will actually just cancel right out. I'm going to have the one divided by the other, and we get a change in y of 120 meters. Now, does that make sense? Well, if the gravity is 1/6 that of Earth, and this one reached 20 meters, it is likely that the ball will travel 6 times that 20 meters on the moon. And in fact, it does. Okay, we've proven it mathematically. It's a little bit tougher to try and prove it conceptually, but that is the case, is that it will travel roughly 6 times as high.